They are some of the oldest mountains on Earth. Born hundreds of millions of years ago, molded and shaped over eons by myriad geologic forces. Some cataclysmic in their effect, some gentle. Once reaching stupendous heights, the mountains we call Appalachians are shadows of their ancient past, worn away by wind, water, and ice over a span of time that defies comprehension. Life took hold here hundreds of millions of years ago. Beginning with the smallest organisms, the region today is recognized worldwide for its unusual beauty and rich biological diversity. It is a place that drew humans to its hollows, coves, forests, and fields several thousand years ago. And it is a place where people continue to live, using the land's resources for subsistence, economic and recreational purposes, many unaware of the ancient geologic forces that created this life-sustaining landscape. Yet even now, geologic forces continue to change the land, changes that may go unnoticed during a single lifetime. In a world where the only constant is change, the landscape we see today will wear a different face in the future. The Southern Appalachians span an area from Virginia to Alabama. Great Smoky Mountains National Park, the Blue Ridge Parkway, national forests, and many other recreation areas are located here. For more than a century, geologists have mapped, measured, and sampled the area's rocks, collecting data that reveal the story of Earth's development over the last billion years. Through their work, we've learned how minerals formed and why certain metals are found in certain places, why some soils are fertile and others are not suitable for farming. We have discovered why species of plants and animals survive in specific environments and nowhere else. All have answers connected to ancient geologic processes.
To me, what is really fascinating about being a geologist is you are an Earth historian, and really what you're doing is putting together an incredibly long period of change, from the movement of continents, the forming of tremendous ancient seas which covered vast areas, and then those seas drying up and turning into mountains. This is a cycle which is repeated over and over again, and the thought that many millions of years ago Africa was right off the east coast of the United States, and then the entire Atlantic Ocean was formed after that, and all of the implications that it has in terms of the distribution of rock types, the geologic structures that we see. All of these come together in a coherent picture that the geologist tries to put together to understand many of the ways in which geology influences our lives.
More than 1 billion years ago, all the continents on Earth had combined into a single supercontinent, surrounded by a single ocean. Rocks at the core of the Appalachian Mountains were once part of this landmass. At Blowing Rock, near the Blue Ridge Parkway in North Carolina, rocks of the ancient supercontinent can be seen at the surface. About 750 million years ago, the supercontinent began to change. Forces deep within the Earth caused the continental crust to thin, fracture, and pull apart. Lava moved up through the fractures and flowed across the surface. Today, soils from the weathered remains of some of these volcanic rocks support oak forests. Other types of lava built up volcanic mountains. Some eruptions were explosive. Geologists discovered evidence of these past volcanoes in rocks at White Top Mountain in southern Virginia. Some of the rocks contain angular fragments that had cooled and solidified, then later broke up and were engulfed in the lava flow. Others contain small, irregular, mineral-filled holes that formed as gases bubbled up through hot lava. As the continental crust fractured, seawater filled a deepening basin known as the Ocoee, near the margin of the continent in what is now the western Carolinas, eastern Tennessee, and northern Georgia. As the basin continued to sink, sediments carried by rivers from the surrounding mountains spread out in layers on the basin floor. Over a long period of time, probably millions of years, the basin filled with thick layers of sediments. Sand, clay, and pebbles deposited in the Ocoee Basin at this time eventually became the bedrock of the Great Smoky and Blue Ridge Mountains. Within these sediments, minerals were deposited, minerals that have had a powerful influence on human activities in this region. In 1843, a prospector looking for gold near Ducktown, Tennessee, found rich deposits of copper instead. Disappointed, he moved on. But within 7 years, others recognized the economic significance of his discovery, and mining began. In time, the Copper Basin became the largest metal mining district in the southeastern United States. For years, geologists have worked to unravel the mystery of how copper came to be deposited here. In the late 1970s, researchers using deep ocean submersibles provided an answer. Diving deep into the utter blackness of the ocean, researchers discovered tall chimneys they named black smokers. They form when hot fluids containing dissolved elements from deep in the earth, such as metals and sulfur, escape through vents onto the ocean floor. As soon as the fluids encounter cold water, the elements precipitate out and become solid. Over time, extensive deposits are formed. Based on these observations, scientists now believe many copper deposits in the Southern Appalachians formed from black smokers in the ancient Ocoee Basin. The copper used to make electrical wires in your house may have originated at the bottom of an ancient ocean. Natural resources such as copper benefit humans. Yet removing resources from the land sometimes adversely affects the environment. In the Copper Basin during the early days of mining, few realized mining and smelting could harm the environment. Rocks containing ore were roasted on open fires to extract copper, which released acidic sulfur dioxide fumes into the air. The fumes sterilized the surrounding soil, and over time, some 23,000 acres became barren, completely devoid of plant life, and scarred by deep gullies. Around 1900, concerned citizens filed lawsuits protesting the environmental degradation. This led to the development of a method to convert sulfur dioxide into sulfuric acid, which is used to make fertilizer. Release of acid into the atmosphere ceased. Restoration of the basin began in the 1930s, but it was not until the 70s, when updated techniques were used, that trees began to take hold. From a devastated area so large it could be seen from space, to an area where millions of trees and shrubs have now been planted, the Copper Basin is an environment in recovery. Another significant source of sulfur in the Copper Basin is the mineral pyrite, commonly known as fool's gold.
Pyrite cubes are scattered throughout many of the rocks of Copper Basin away from the copper deposits. When pyrite is exposed to air and water, it breaks down and releases sulfur and iron. The result is rusty iron stains on the rocks and sulfuric acid in the streams. Any disturbances that expose more rock surfaces to air and water, like road construction or landslides, can affect surface water runoff enough to kill aquatic life in streams below the disturbance.
To remove acid from streams affected by the disturbance of pyrite and other sulfide minerals, scientists have devised a method of neutralizing the acid using a substance that, like the copper ore, had its origins at the bottom of an ancient sea, limestone. Limestone is created when remains of marine plants and animals accumulate on the floor of shallow oceans. The limestone found in the Southern Appalachians formed when the continents drifted apart and a vast, shallow sea covered most of the North American continental plate. Used for a wide variety of purposes, from road building to the manufacture of concrete, the chemical composition of limestone makes it the perfect material for neutralizing sulfuric acid. On the Ocoee River in Tennessee, construction of the Olympic whitewater course in 1995 put limestone to the test. Here, the stream bed contains pyrite-bearing rocks, which naturally release acid. When these rocks are disturbed, larger amounts of acid are released into the water. To head off a potential environmental problem, limestone was added to the stream bed during construction of the course to neutralize acid as it develops. Today, geologists continue to expand our understanding, helping ward off future problems. Mapping rocks can help predict where pyritic layers are likely to occur, while studies of water chemistry further our awareness of how sulfide minerals interact with the environment. Studies also help determine whether the source of acid in a particular environment comes from rocks or from atmospheric pollution.
The sampling that we're doing now gives us a snapshot of the environmental signature of the rocks and the waters and the mineral deposits and how they've behaved up until this point in time. And by understanding the processes that go on, the interactions between rocks and water, it'll help us be able to predict interactions between rock and water in the future.
Other geologic studies provide insight into how rocks that formed on ancient sea floors became the mountains and valleys of today. About 470 million years ago, the North American and African continental plates, which had been moving away from each other since the time the Ocoee Basin formed, reversed direction, and fragments of oceanic crust, islands, and other small continental masses collided with the eastern margin of ancestral North America. After this time, plants appeared on land, followed by insects and amphibians. Then, about 270 million years ago, the continents ancestral to North America and Africa collided. Huge masses of rock slid westward across what is now North America, piling up to form the mountains we know as the Appalachians. As blocks of continental crust rode across one another, some rocks became so hot they melted. Volcanoes and lava flows occur when molten rock reaches the Earth's surface. But molten rock can also remain deep below ground. Cooling slowly over time, it forms large bodies of coarse-grained rock called plutons. Composed of granite and similar rocks, plutons are scattered throughout the Southern Appalachians. While some still lie hidden by earth and rock, others have been exposed by erosion. Weathering of some plutons forms unusual-looking smooth-sided domes, like looking glass rock, seen from the Blue Ridge Parkway south of Asheville, North Carolina. Granite is used for buildings, statues, and monuments. In Mount Airy, North Carolina, where granite is quarried, some homes and churches are built with this native stone. During the continental collision, some rocks were exposed to high temperatures, but did not melt completely. Instead, these rocks took on a toothpaste-like consistency and were squeezed into folds and swirls of light and dark-colored minerals, forming metamorphic rock. Under relatively low metamorphic temperatures and pressures, very fine-grained rocks, such as shale, recrystallize into slate that splits into thin, smooth layers. Over time, these rocks may break into many small pieces that make excellent skipping stones. But serious problems may arise when large sections of these rocks are steeply inclined or tipped. During periods of heavy rainfall, these rocks are prone to landslides. Some rock layers of the Southern Appalachians have many folds and faults that formed during the continental collision. Faults are major breaks or fractures in the Earth's crust that can cause one side of the break to ride over the other. This movement causes earthquakes, which during the time of continental collision would have been a common occurrence in the region. Today in the Southern Appalachians, large earthquakes rarely occur. In Cades Cove, located in Great Smoky Mountains National Park, the effects of faulting are evident. Here, older rocks of the surrounding mountains moved over younger rocks on the Great Smoky Fault. Erosion then carved an opening to expose younger rocks below the fault in a feature called a geologic window. Throughout the region, many faults have been identified. One at Linville Falls, north of Asheville, North Carolina, illustrates powerful geologic forces that pushed huge masses of rock distances of 60 miles or more. The ledge that forms the falls and the gorge below are younger than the rocks making up the surrounding mountains. After the continents collided, the process reversed itself. About 240 million years ago, the beginning of the age of dinosaurs, a new ocean basin began to form, the present-day Atlantic. As time passed, the Appalachians were slowly reshaped by erosion. Limestone weathered to create the lime-rich soil so common in the fertile farmland of the region. And caves and sinkholes were formed that today contain unique living communities. Soft rocks like limestone and shale eroded away, while hard rocks like sandstone resisted weathering, creating outcrops and cliffs that are habitats for rare plants and animals. Geologically, it was a period of calm in the region. And then came the Ice Age. 4 times during the past 2 to 3 million years, great sheets of ice advanced steadily southward from the polar region. While glaciers did not extend as far as the Southern Appalachians, they triggered a change in climate that had a great and lasting impact on the region. Animals and plants migrated southward to escape the deadly freeze. Species such as the saw-whet owl, the northern flying squirrel, the red spruce, and Fraser fir moved into the area from the north. Establishing themselves in the Southern Appalachians, they can be found to this day at higher elevations. Effects of the Ice Age are also revealed in the rocks. When water freezes in cracks or between layers of rock, it expands, gradually wedging the rocks apart. During the Ice Age, repeated freeze and thaw cycles split rocks, creating piles of boulders. In the Southern Appalachians, concentrations of boulders can be seen on some forested mountainsides, a silent testament to the extreme cold of the Ice Age. Other natural processes that are more subtle, yet nonetheless persistent, are also significant instruments of change in the mountains. Mosses and lichens break rocks down over time and help create soil. Plants growing in rock fractures slowly widen them. Wind, water, and ice continue the process of eroding rocks into tiny bits of sand or sediment. Carried by streams and rivers toward the sea, these sediments eventually end up where most of them started, as deposits on the sea floor. The northeast-southwest orientation of the Southern Appalachians affects the direction sediments travel. Those from the western flanks of the mountains are transported into the Gulf of Mexico, while those on the eastern side are carried to the Atlantic. But the position of valleys and ridges in the region have affected more than just sediment transport. The mountains form a natural barrier to the west, defining the main routes of human travel, communication, and settlement. Over 1,000 years ago, the Cherokee people arrived. Finding a bountiful land that sustained both body and soul, they hunted and fished, collected berries and herbs, and in mountain streams and rivers, they found gold. For the Cherokee, gold did not have the same significance as it did for the region's European settlers. But the presence of gold on Cherokee land led to profound and tragic changes to the Cherokee way of life. In 1829, newspaper articles describing vast deposits of gold on Cherokee land brought thousands of non-native people to the area with dreams of quick riches. They washed gravel from the banks of the streams in their search for gold and took over land ancestral to the Cherokee. The frenzy caused by the discovery of gold hastened the removal of the Cherokee in 1838. On a forced march, known as the Trail of Tears, the United States government sent most of the Cherokee Nation westward to Oklahoma. Along the way, many people died, and those who made it to Oklahoma found the land completely different from the one they were forced to leave behind. The Cherokee who remained in the Southern Appalachians continued to see an influx of settlers into the area. Those who came were mostly farmers, looking for good land and solitude. The topography, as well as fertile soil and an abundance of animals and plants, met their needs, and many found a sustainable way of life, just as the Cherokee had for generations. Today, the Southern Appalachians continue to change. The cycle of life on Earth and the age-old processes of building and breaking down are ongoing, never-ending. Long after we have lived our lives, rocks will continue to be eroded into sediments, or be melted to form lava, or be pushed great distances or to great heights by powerful geological forces. Our knowledge of Earth's history is a window into the past and the future. By studying the Earth, we can decipher and reconstruct the changes that occurred over billions of years and also predict future changes, changes that are inevitable on this dynamic Earth.